Hello everybody, I'm back with one more example of how to calculate transverse shear stress, but this time on an unsymmetric cross section, T cross section as shown here in this video. Now, we have actually used this T with the dimensions before, so I thought it's a good idea to just be efficient and reuse the same cross section. So you guys recall, if you go actually to the video called Bending Stress Number 2 that I sent you last week, you'll see that we determined that the centroid is going to be 5 inches from the reference, and we calculated the moment of inertia with respect to the neutral axis actually. So this is actually a moment of inertia with respect to the neutral axis, which came out to be 60.67 inches to the power 4. So now I want to, kind of have another beam with some loading. This loading actually looks familiar to you guys. We've used this loading before, right? So I want to use this loading and show you that based on the loading that we have here, and this is 2,000 pound also, right? We want to calculate the maximum shear stress, and the maximum shear stress actually happens right here on the neutral axis. And also I want to show you the variation of the shear stress along depth. You'll see in a minute that actually the shear stress right between the interface of the flange and the web is going to change, and I'll show you why that's the case. So I'm going to take a pause and show you how we can, actually redraw the flange and actually the section that we want to calculate the first moment of area. Okay, so we want to find actually Q max. Remember that we have to use the tau equal VQ over IT, the shear formula. So where is Q max? Q max happens right on the neutral axis, right here. Okay, so now remember, how do we calculate Q? Q, we have to, because we are on the neutral axis, so it doesn't matter if you use the shade the area to the top fiber actually, or shade area to the bottom fiber, doesn't matter. If you decide to use this area to calculate Q, you have to use the summation equation, which doesn't make sense because you have two pieces, one piece here and the other piece is the flange here. Not a good idea, because we'll get the same result if we shade below and use this area. So I decided to use this area, so I called it Y bar, it's just one area, times A star. A star is the area of this section, which is 5 by 1, right? So that's 5 inches squared, that's the area. And Y bar is what? The distance from the centroid of the shaded area to the neutral axis. So that's half of 5, that becomes 2.5 inches. So that comes out to be 12.5 inch cube, and then we are all set. The shear load, remember, is 4,000 maximum shear load. So we put it there. Remember the unit worked out before, times 12.5 divided by the moment of inertia that we calculated earlier, and you can check that video. And 1 inch for what? 1 inch is T. So shear stress happens right here, and that's T of equal 1. So that comes out to be 824 psi. So now what I want to show you next is what happens at the interface, at this point, the value of the shear stress. In other words, the point could be what? A little bit above the interface, so it would be on what? On the flange. On the flange, T is 8 inches. But when you look at the same point a little bit, maybe 1 millimeter, very tiny distance below the interface, then the T becomes 1 inches because you are on the web. So let me pause again and go to the next page and draw some pictures, and then I'll be back. Okay, so I basically drew these pictures for you here and the calculations. So our objective now is to find Q at A, right at the interface between the flange and the web. So how do we do that? Q at A, what do? We shade the area to the nearest fiber because we are above the neutral axis. Remember, the neutral axis is here, so we go to the nearest fiber. So that becomes our area, which I called it A star, right? And Y bar would be what? The distance from that centroid to the neutral axis. So 8 inches squared for the area and 1.5. That gives me a 12-inch cube. Now, this is the interesting part. If A happens to be, well, we know A is on the interface, but imagine if A was like 1 millimeter above the interface, so it was on the flange. So if A is on the flange, T becomes what? 8 inches, right? Right, that's T. Therefore, if you calculate tau sub A based on the maximum shear load, the 12-inch cube that we got here, the 60.67, which is always a fixed number here, but T is 8. We get 99 psi. But now, what if A happens to be on the web? So imagine if A was 1 millimeter below and it was on the web, then T becomes 1. If you do the calculation, you get basically 8 times. So you see 792 is what? 8 times what? 99. Okay, so there is a big jump of in shear stress. So the last thing I want to show you here is actually the shear stress distribution. So we know that along the depth of this cross section, along the depth, we have to start at 0 shear stress and end to 0 shear stress. Remember, shear stress should be 0 here and 0 here. So look, we know that shear stress changes parabolically, reaches a value of what, 99, the one on the flange, and then there is a big jump when we go right below that to 792, and then it parabolically increases, reaches the tau max that I calculated for you over here, right, the 824. Here we go, and then parabolically it goes back to what, 0. So the last thing I want to show you in another video is how would that work, how the shear stress changes if we had, say, an I-beam. So if we just added a flange below this and we made this, the T, an I-beam. In that case, you probably have an idea already how it should look like. But you'll see that in the next video. Thanks for watching and listening.